Hi, everyone. So a number of you have asked me to make a flux balance model involving an example that's a little more difficult than the ones that we covered in class that you can use to study from. So I'm going to talk about how we calculate fluxes in the context of glycolysis, since this is one of the trickier kinds of examples as a result of the aldolase step. So just as a brief reminder here, of course, when we are dealing with flux balance problems, we have carbon that's coming into and out of a system here. In this particular case, we'll have glucose coming in and lactate going out, and everything inside the system has got to be in steady state equilibrium. Okay, so that's the start of these calculations. Now, before you get going on anything, one of the things that you can do is you got to keep track of where all the nucleotides are made and the cofactors are made and consumed. Frequently, those steps are controlling fluxes in the system. So of course we have ATP going in the hexokinase step and in the FBP step, and we have it being consumed or produced here in the two payoff steps. We also have NADH being made by GAPDH, and we have it being consumed in the step making lactate dehydrogenase step. Now, in all cases, we can define our systems, we can constrain them by what's coming in. So in this case, V0, and what's coming out. In this case, we're going to be maximizing for this output through, we'll call this the OB. Within the system, then, we can define the remaining fluxes by just numbering them up, V1 to V2, V3, V4, for example. And if we go through and we label all the reactions in our system, then we can go and start to set constraints on what we can see in our pathways. So just in looking at this network, we can tell a few things about this. One is that we can say that V0 must equal V1, which equals V2, which equals V3, must equal V4. And we can tell that because if any of these fluxes weren't even, then we would end up with a buildup of one of our intermediates, which would violate our steady state equilibrium assumption that we're working on. So similarly, we can also see that V6 must equal V7, which must equal V8, which must equal V9, which must equal V10 and VOB. And this is similar kind of logic where we can tell that these have to be in equilibrium, otherwise we end up with a buildup of a steady state intermediate. Now, what's not equal in the system is V4 isn't equal to V6, okay? And the reason it's not equal is because of this aldolase step here. This aldolase step produces not one, but two products here. So we have glyceraldehyde phosphate, and we got triose phosphate isomerase, and dihydroxyacetone phosphate, and the triose phosphate isomerase step is then reequilibrating them. The net result is, since dihydroxyacetone phosphate and glyceraldehyde phosphate are made at the same rate, then the downstream fluxes have to be faster to account for the removal of this carbon from the system. So how can we say that algebraically? So, well, we can say we can define this in terms of V6. V6 that we can see here must equal the rates at which glyceraldehyde phosphate is made minus the rates that it's consumed. So we can say that V6, actually, let me define it this way. We'll say that the rate of the production of, or the rate of change of glyceraldehyde phosphate with respect to time, dAdP dt has got to equal the rates that it's made, which we can collect up when we say V4 plus V5. And then it's all of that minus the rate that it's consumed, which is V6. So we can collect our terms here. We know that this has got to equal 0 for this to be at steady state. And we say that V6 is equal to V4 plus V5. Okay. The other way we can say that is if V4 it must equal V5. We can tell that here because the rate that dihydroxyacetone phosphate is made and consumed must be equal. So in that case, we can say that V6 is equal to 2 times V4. Or if we want to simplify that and use our equivalencies that we've drawn before, we can say that our objective function VOB must equal 2 times V0. Okay, this is a great example of how keeping track of this complication here at the aldolase step and the triose phosphate isomerase helps you solve one of the tricky parts in glycolysis, which is understanding that fluxes out have to be twice the flux in. And this makes sense. So for every mole of glucose that you got coming in, if it's all going out as lactate, it's got to be 2 moles of lactate.